Welcome back to the Deep Dive. Today we're heading out onto the high seas. We're going to tackle one of the biggest challenges facing global commerce right now.
Decarbonization of the shipping industry.
Exactly.
Yeah.
I mean, you look at the regulations, things like the IMO's EEXI and CII, and you realize pretty quickly that, just tweaking the old systems isn't going to cut it anymore.
No, the clock is ticking. The pressure is on.
And for a while, it seemed like LNG, liquefied natural gas, was the answer.
Well, it was a lifeline, a necessary bridge fuel to get things moving. And it is a massive step. I mean, switching to LNG, it immediately slashes CO2 by up to 25%.
And it gets rid of the really nasty stuff, right?
Oh, completely. Yeah. It virtually eliminates sulfur oxides and all that particulate matter.
But like you said, it's a stepping stone. Just changing the fuel doesn't really optimize the whole system. And that, I think, is the core of our deep dive today.
Right.
We're looking at a system that represents a whole architectural revolution. Dual fuel electric plus or DFE plus.
Precisely. We have to go beyond just what's happening in the combustion chamber. We have to rethink how power gets generated and how it's delivered to the propeller.
So our mission today is to unpack DFE plus brain, this radical integration of electric power, energy storage, and LNG engines.
And see how it all comes together to solve efficiency and compliance problems all at once.
Okay, before we dive into the nuts and bolts of the plus, let's just get some context. Electric propulsion, it sounds futuristic, but it's really not new, is it?
Not at all. The concept goes way back, well into the 19th century. It was always used for specialized vessels, icebreakers, cruise ships.
Places where you need a lot of control and torque.
Exactly. Then for commercial shipping, we saw the shift from old steam turbines to dual fuel diesel electric DFDE. That was good. But DFE plus is the next evolution. It's all about maximizing efficiency by bringing in modern electrical components.
And crucially, massive energy storage.
That's the plus.
Okay, let's start with the architecture itself. DFE plus is a fully integrated electric power and propulsion architecture.
So the electricity is generated on board.
Yes, and that's the fundamental difference. In a traditional ship, the engine is physically linked to the propeller shaft. So if you want to go slower,
you have to slow the engine down.
Right. And that means you're almost always running it at a really inefficient RPM.
It's like driving your car in stop and go traffic. You're just burning gas for no reason.
You've just hit the key insight. The biggest advantage of DFE Plus is that it decouples engine speed from propeller speed.
So the generators can just run at their optimal load point all the time.
All the time. Think about that car analogy again. Your engine is most efficient when it's cruising on the highway, right?
Mm-hmm.
In a DFE Plus ship, the engine is only making electricity. So it can stay locked into that perfect fuel-sipping RPM, whether the ship is crawling into port or going full steam ahead. That saves a huge amount of fuel and reduces wear and tear.
So what are these prime movers? What are the generators feeding this electric grid? We're talking about very high efficiency, 4-stroke dual fuel engines. They're the power source, running mostly on LNG, but they do need a tiny injection of liquid pilot fuel just to kick off combustion.
And the real advance here isn't just that they burn LNG, but how they do it.
That's right. It all comes back to a huge environmental concern: methane slip.
Explain that, because it's a big deal.
It's a massive deal. LNG is great for CO2, but it's mostly methane. And if any of that unburned methane escapes the engine, that's the slip, it's a problem. Methane is a greenhouse gas that is, over 80 times more potent than CO2 over a 20-year period.
Wow, 80 times. So if your engine is leaky, you could be wiping out all the environmental benefits of switching in the first place.
Precisely. So this latest generation of engines, they use really advanced combustion strategies, especially with that pilot fuel injection, to pretty much eliminate that slip.
And the economics must be pretty compelling too.
Oh, absolutely. We saw one study that showed a vessel with this DF architecture saved about $1.37 million per trip compared to just running on conventional heavy fuel oil.
That is a number that gets your attention.
It definitely changes the conversation about the initial investment.
Okay, so you've got multiple generators creating this huge AC electrical grid. How do you manage all that? What keeps the system stable?
That's the job of the dynamic AC or DAC systems. Think of them as the grid managers. They use sophisticated power electronics to constantly monitor and maintain a stable voltage and frequency across the whole grid.
Like a shock absorber for the electrical system.
A very finely tuned one, yes. Without that stability, you can't get optimal load sharing between the generators. The DAC makes sure every engine is running at its most efficient point all the time.
And then guiding all of this is the real brain of the operation, the the Propulsion Energy Management System, or PMS.
The PMS is the conductor of the orchestra. It's the software control unit that coordinates everything: the engines, the DIC, and critically, the batteries.
And these modern PMs, they're not just reacting, are they? They're predictive.
They are. They use data analytics and algorithms for load forecasting. So if the system knows from the sea state that a big wave is about to hit and increase the load,
It can prepare for it.
it can preemptively draw a little power from the batteries before the peak hits. This proactive adaptation avoids those sudden, inefficient spikes in engine operation.
And smarter software means real fuel savings.
It does. And optimized PMs alone can achieve fuel savings of up to, I think it's 4.8% per voyage. That's a huge gain just from better control.
Okay, let's get to the plus components. Starting with the battery energy storage systems, the BEEXI. This is what enables true hybridization.
The batteries are all about resilience. Their biggest job is something called peak shaving.
Meaning,
When the ship needs a sudden burst of power, say for a fast maneuver or using a thruster, that huge transient load can be handled instantly by the batteries.
instead of forcing an engine to ramp up inefficiently.
Exactly. The battery handles the spike and the main engines just keep humming along in their happy place. It saves fuel and reduces stress on the machinery.
And there's a big safety function too. You called it spinning reserve. What does that mean in practice?
It's basically an instantaneous backup. If a main generator suddenly fails, the battery is already online and can instantly supply power to prevent a blackout. It's a massive safety and redundancy feature.
And the real world numbers on this are, well, they're staggering.
They really are. There was a case with a hybrid LNG tugboat. It saw an average CO2 reduction of nearly 65% and lowered its daily fuel cost by almost 68% compared to a diesel system.
Those are not small changes.
No, that's a fundamental shift.
Okay, from power generation to power delivery, let's talk motors. Permanent magnet motors, or PMMs, are replacing the old induction motors. Why?
It's just beautiful physics, really. PMMs use powerful permanent magnets in the rotor. This means they don't need any external electricity to create their magnetic field.
So less electricity needed overall.
Right, no wasted energy creating that field. It means PMMs can hit these incredible efficiency numbers like 98 or 99%. That translates directly into less fuel being burned by the engines to get the same push.
And you mentioned they're also more compact.
Much more. More power in a smaller, lighter package. This gives ship designers a lot more flexibility in how they lay out the vessel.
And these PMMs are often put inside azipods, right? The steerable pods under the hull.
That's right. Azipods get rid of the need for a long propeller shaft and a rudder. The motor is inside the pod and the whole unit can rotate 360 degrees.
Which gives you incredible maneuverability.
Phenomenal. A ship with azipods can practically move sideways. It means less need for tugboats in port, which is another cost saving. And for something like an ice class vessel, that ability to direct thrust anywhere is a complete game changer for breaking ice.
Okay, let's pull all these threads together. You've got efficient engines, a stable grid, a smart PMS managing everything, batteries for buffering, and these ultra-efficient motors. What's the fundamental change here?
The change is that the vessel is no longer a collection of separate mechanical parts. It's a single, cohesive electrical ecosystem.
A floating smart grid.
A floating smart grid, exactly. It can shift power sources, maintain optimal engine health, and slash fuel burn no matter what it's doing.
Which brings us right back to where we started, the EEXI and CII regulations.
And this system dramatically improves those ratings. The efficiency and the use of LNG give it better scores right away. And with the batteries, you can run in a silent, zero-emission mode in port.
Which is becoming more and more critical for local air quality rules.
Absolutely.
Now we have to talk about the elephant in the room, the cost. All this tech, it sounds expensive. The initial capital expenditure, the CapEx, must be higher.
It is. That's the honest truth. The upfront cost for a DFE Plus system is higher. It's a big initial investment.
So what's the counter argument? Does it only make sense for the huge shipping lines?
That's a really important question. You have to look at the total cost over the ship's entire life. The long-term operational expenditure, or OPEX, so the savings are just enormous from fuel.
Massive fuel savings, yes, but also much lower maintenance costs. because the engines aren't being stressed all the time. Over the vessel's lifespan, those OPEX savings almost always offset the higher CapEx.
So the complexity that gives you the savings is also the biggest challenge to getting it adopted.
It is. There's the technical hurdle of making sure all these complex systems communicate perfectly, and the regulators have to keep up, especially with safety rules for batteries.
And then there's the human element.
Without a doubt. The biggest barrier might be people. This requires a different kind of crew with specialized training. You're moving from a mechanical plant to a sophisticated power electronic system.
You need technicians who understand grid management and software, not just wrenches and pistons.
Exactly. And that's a big investment in your workforce.
Okay, let's bring this deep dive home. What's the final takeaway for you, the listener, about this DFE Plus platform? For me, it's that DFE Plus is really the template for the future of shipping. It's not just a fuel choice, it's a whole system designed for resilience, for maneuverability, and for long-term economic viability. This electric architecture is the foundation for everything that comes next.
And if you're a stakeholder, an owner, or an operator, the message is clear. Look beyond the sticker price. You have to do a full life cycle cost analysis. And you need to factor in what's coming, like carbon taxes that are going to heavily penalize less efficient ships.
Agreed. The future cost of not complying will be far, far higher than the initial investment in this kind of tech.
Okay, so let's unpack one last thing for the future. The whole DFE Plus platform is adaptable because its power is electric generation, not a direct mechanical drive. So, what does it mean that this system is already designed to allow for an easier switch to future zero carbon fuels? Think green hydrogen or ammonia. You could just swap out the generators when that tech is ready. That flexible architecture is already future-proofing these vessels.
That's a whole new deep dive for another time.